This example is on a little elevated challenge. So this is a definite integral with boundaries 0 to 3 square root of 3 over 2. The integrand itself is x cubed divided by the quantity 4x squared plus 9 raised to the power of 3/2 dx. Okay, we need to evaluate this thing. So I'm looking at this integral, and the first thing I noticed that I don't see any recognizable radical. This radical doesn't look like anything that we've done before. So let's try to rewrite this integral in a slightly different manner. Okay, so we call it I, and it will be the integral from 0 to 3 square root of 3 over 2. The denominator will be x cubed dx. The numerator, I'm sorry, I said denominator. The denominator has a rational exponent with 2 as the denominator. It means that it's really the square root of 4x squared plus 9 raised to the third power. Now I could have written it as the square root of the quantity 4x cubed plus 9 raised to the third power inside the radicand, but I did it intentionally. I wrote it intentionally this way because I want to substitute the radical before cubing it, okay, and cube the outcome. I'm still not out of the woods yet because this is still not one of the 3 radicals that we had earlier, okay? So I need to do something to 4x squared. And I'm saying to myself, if instead of 4x squared I had something squared, like z squared or u squared, then I have the radical, the square root of z squared plus 9 or z squared plus 3 squared. I can deal with that. So this will be the substitution. I'm going to let, since I'm going to use u down the road, I'm going to choose z, and I'm going to let z equals, or z squared equal 2, z squared equal 4x squared, or z by itself equal 2x. And of course, now I need to take care of dx, so dz equals 2dx, and therefore dx by itself equals 1/2 dz. So what about x cubed? Well, since x equals z over 2, then x cubed is z over 2 cubed, and the denominator x cubed dx will be z over 2 cubed dz over 2. Okay, let's do some work here. Z cubed dz, 2 cubed is 8 times 2 is 16. So we have z cubed dz over 16. This will be the numerator, x cubed dx. We took care of that part. What about the denominator? What about the boundaries? Well, let's take care of the denominator first, and then worry about the boundaries. Okay, so what is the denominator? The denominator is the square root of 4x squared plus 9 cubed. After the substitution, we are looking at z squared plus 9 cubed. Wow, that's not bad at all, right? So this is the denominator, this is the numerator. Boundaries. Okay, when x equals 0, z equals 2 times 0, z equals 0. When x equals 3, square root of 3 over 2, well, remember z is 2x, so z equals simply 3 square root of 3. So the integral with the new address will be the boundaries 0 to 3 square root of 3. Numerator will be 1 over 16, take the 16 out, z cubed dz. Could have, should have taken this outside the integral altogether. The denominator will be the square root of z squared plus, I'll write it as 3 squared instead of 9, all of it cube, okay? And because I forgot to take the 16, 1 over 16 outside, I'll write it again. This time I'll do it. At this point, I'm ready to do the trig substitution. This looks like the kind of substitution where we substitute with the tangent. So the second substitution coming up, and we let z equal, because we have 3 squared, 3 tangent theta. Okay, and we need to replace dz, and dz will be replaced by 3. The derivative of the tangent is the secant squared d theta. Go ahead.
I was going to ask, why'd you even switch it to z? Why can't you just bring the 4 out and then say a squared is...
Very good point. I could have bring the 4 out and have x squared plus 9 over 4 and let a equal 3 over 2. 9 over 4 is 3 over 2 squared. That's another possibility. Yes, that would be an alternative. We'll save one step. Okay, I don't know if did you understand the question or the comment, suggestion? This is an excellent suggestion. And matter of fact, I was planning to show you something like that on Tuesday. But it's also, sometimes it won't be so obvious. For instance, if 9 was not, well, no, I'll stay with it. It's a good point, John. So yeah, this is a pretty good alternative. But sometimes it's easier to do it this way, as the idea was to bring it to a recognizable pattern. We have 3 trig substitution, and this is something we recognize.
How come you have to pull up the 4? Like, why can't you just say, because we were going to say 3 is going to be a anyways, why not just multiply 3 times 4, and that's,
No, you actually need to divide, because remember, you have to have something squared plus a number squared. So a variable squared plus a number squared will give you the substitution. In the pattern is on the first page. You want to write everything like that. Either like this, if I name it as 1, 2, and 3, those are the 3 forms. So in our case, well, this will be a squared plus x squared, or x squared plus a squared. You need to have a variable squared plus a number squared. So you have 4x squared. So either do what I did, replace 4x squared with z squared, or do what John did, factor out the 4. But if you factor out the 4, then instead of 9, you have 9 over 4.
Does the constant, or the 4, like, make it screwy if you leave it there? Like, because, I'm understand, like, that's the form.
Right.
But, when you're substituting, because technically you're just substituting one of the substitutions for x, and then you're going to take that, and then, why not? You can't multiply the constant of 4, because technically it's still in form. It's just
You technically can do that. You can do that, but you need to be careful when you do the back substitution. Remember, those are all intermediate values. So eventually you're going to come up with tangent theta. And in the solution, you're probably going to have either secant theta or tangent theta or any other thing. And you need to you need to back substitute from the variable theta to the variable x. Well, it will be more difficult if you leave it before there. And that's why it is easier to substitute if you write it, if you go back and use this z squared plus 3 squared, than x squared plus 9 over 4, 3 over 2 squared. You can do with the 3 over 2, but what you just suggested, even though it's possible, it's still harder. Okay, so let's write everything now in terms of theta. So let's look at the denominator. Well, the denominator, remember, was z squared plus 3 squared cube. After the substitution, we're looking at the square root of 9 tangent squared plus 9, all of it is cube, and you factor out the square root of 9, so you have 3 outside, and here you end up having tangent squared plus 1, which is the secant squared, but everything is cube. So you end up having 3, and here's the square root of secant squared, so you have 3 secant cube. So this is the denominator. So numerator dz, well, we have still z cube. Okay, so what is z cube? Z cube will be simply 3 tangent cubes. So now let's write the integral. Remember, we have 1/16 outside. Boundaries. Forgot the boundaries. So we need to do boundaries here. So what are the boundaries? In the morning, I try to leave the boundaries and go all the way to the end, and then at the end, go and retrace the boundaries, and we concluded that it's more difficult. It's better to propagate the boundaries as we make substitution. So let's see. The boundaries were z equals 0 and z equals 3 square root of 3. So let's start with z equals 0. Since z is 3 tangent theta equals 0, and therefore theta equals 0, right? On the interval, remember, tangent goes from negative pi over 2 to positive pi over 2. When z equals 3 square root of 3, then 3 tangent theta equals 3 square root of 3, or tangent theta equals square root of 3, so theta equals what? What angle in radian measure produce tangent that equals square root of 3? Well, that will be pi over 3, or 60 degrees. So theta 1 will be 0, and theta 2 will be pi over 3. And now we're ready to rewrite the integral. We have 1 over 16, the boundaries, 0 to pi over 3. Numerator, z cube, well, this will be 3 tangent theta cube. Let me keep it like that. dz is 3 secant squared theta d theta. And the denominator is 3 secant theta cube. And now let's see if we can simplify. Well, you know that you have 3 cube over 3 cube, and you have 3 here, so outside we have 3 over 16, right? The integral we have tangent cube d theta, and no, we have tangent cube secant theta. No, this is secant squared divided by secant cube. So we have tangent cube d theta divided by secant theta. Okay? In the morning I did it one way. This time I'm going to do it a different way. I'm going to write it the following. This will be 3/16. The integral, the boundaries are 0 to pi over 3. I'm going to simplify everything in terms of sine and cosine. So tangent cube will be sine cube over cosine cube. 1/the secant is the cosine, right? So we have cosine theta d theta, like so. Again, tangent cube is sine cube over cosine cube, and 1/the secant is the cosine. So let's see where we're going with this. We end up having sine squared divided by the cosine squared, right? I'm sorry, we end up having sine cubed divided by the cosine squared. I'll break it down to sine squared theta, sine theta d theta divided by the cosine squared of theta. Now, why did I do it? Because I have odd power over the sine, and sine theta d theta is the differential corresponding to cosine. Okay, again, cosine divided by cosine cube give me cosine squared. Sine cube is sine squared times sine. So I'll write now is 3/16, the integral 0 to pi over 3. Instead of sine squared, I have 1 minus cosine squared of theta divided by the cosine squared, sine theta d theta. We are ready to yet another substitution. Last one. Okay. Where we are, okay, this is what we have. If you look at the bottom, I, the integral, let me rewrite it, is 3/16 1 minus cosine squared over cosine squared sine theta d theta 0 to pi over 3. Our substitution, we let w, since we are running out of the alphabet letter, equal cosine theta, and therefore dw equals negative sine theta d theta. So sine theta d theta equals negative dw. Okay? Boundaries. Okay? When theta equals 0, then w equal cosine of 0 equals 1. When theta equals pi over 3, then w equal cosine of pi over 3. And that would be equal to what? Square root of 3/2, right? Huh? pi over 3 is 1/2. My bad. Pi over 3 is 1/2. So this will be W1, this will be W2. Now, let's get rid of the split and bring it home. So the integral will be 3 over 16. The integral from 1 to pi over 3, 1 minus W squared over W squared, and, I'm sorry? 1 to 1/2. I'm getting a little bit, I'm trying to rush. And sine theta d theta is negative dw. So because of the negative, we're going to flip the boundaries and get rid of the negative. So we go from 1/2 to 1. And look what happened here. We have a common denominator. So this will be 1 over w squared minus 1 dw. And now this is his integral. It will be 3 over 16. This is w to negative 2, so the antiderivative will be negative 1 over w, and this will be simply w, evaluated from 1/2 to 1. We can rewrite it as 3 over 16. This is both of our negative, let's see. I'm trying to see if I got the sign correctly. That's the negative. So this is 1 over w squared. That would be negative. So that's okay. That's okay. Are we okay with the sign here? And this will be what? 3/2 w, right? Oh, no. Sorry. So let's evaluate. For 1, we end up having 1 minus 1. That's 2. For 1/2, we have negative 1/2 minus, no, negative 2. 1 over 1/2 is 2. Negative 2 minus 1/2, like so. Let's see if I got the arithmetic correctly. For 1, we have negative minus negative, and here for 1/2, we have negative 2 minus 1/2. So we'll have 3 over 16, negative 2 here, and minus, this will be minus 5/2. Right? This will be 5/2 minus 2, or 1/2, so we end up having 3 over 32, which happened to be the correct answer. So if you feel like, wow, at the end of this exercise, I told you this is a little bit of a higher level challenge.